Um, I'm just wondering, why don't, since this is a 468 class in which I'm going to be doing some examples, um, it rather than a straight lecture, maybe students would like to ask questions, and in that case, that's just fine. And what I'll do in that case to avoid UNM's FERPA police is I'll just put it on YouTube as a private video and just available to people who have the link, who will be people in this class. In any event, we're recording now, and I thought I would first start out by showing you, let's see, where is it? Yeah, it's right over here, actually. What I did here was I thought I would, here, let me bring this is a MATLAB program that's actually running. That's why it says pause here. It's running and it says busy down there. That's why it says busy. But it's only taking about 4% of the CPU. And so it's incredibly slow. Apparently, MATLAB has the default. The default is to use very little of the CPU unless you use their parallel programming package, which may or may not be included in UNM's version of the license. I don't actually know. I imagine it's included, but I don't know for sure. In any event, this is the delta function formula for, or delta function program that generated this. Now, in fact, you see here, I'm saying this is the first 10,000 terms of the expansion. This is the delta function expression for delta of x minus x prime. And what I did was I set x prime equal to 0 in this thing. And when I originally did this, I did something like 0.1, and I only did 10,000 terms. And so it ran fairly, it didn't take forever. This time I thought, well, let's make it a really finely done graph. And so I did 0.0001 and then 100,000, set this n to go to 100,000. Well, it's been running all day and all afternoon. I started around, I don't know, noon or 1 o'clock. Still running, and I think I'm just going to have to start another program. If I had known that it was going to be so slow, I would have used a simple formula for Pn of 0. It turns out that that is actually those are special values. The odd Pn, if n is odd, Pn of 0 vanishes, and if n is even, it's just a ratio of double factorials. So it's actually simpler than that. And notice here, this is very wasteful programming, because you see, for each, I've got here, I'm redoing I'm calling the Legendre polynomial at each x and at 0 for every y, whereas I could have just called them once up here and done it. And so this is very wasteful programming. What I might do, since you guys, I'm going to pause it. And whoa, Whoa. All right, I'm just gonna stop and do a new one. Well, all right, I'm gonna go back to new plot. Ooh, that's the one I showed you. Right, here it is. Okay, so how would one do this more intelligently? The first is that one would only do this um, uh, in steps of two, because the Legendre polynomials at odd values vanish. Secondly, I would have up here said Px equals Legendre of Px, of P of Nx. Oh, damn it, it is P of Nx, isn't it? So I do have to. Right, all right, so maybe there isn't a simple way of doing that. Well, I'll have to think some more. In any event, we can skip the odd ones. And at the very least, I can pull this down to 0, 1. And I'm going to now run it here. So this is going to run much more quickly. And all right, Houston, we have a problem here. So I'm not going to try to puzzle this through. I thought this would be simple and instructive, but I'm getting it. There's apparently an error in the code, and I'll just have to figure that out and show it to you tomorrow. So let me go just do some examples here. The first one that I thought of doing was let's see. All right, so the first was here, let me show it to you on the screen here. And let me make it bigger. So I think I may have said something about this yesterday, but in any event, let's just go through it. Show that the points x equals plus or minus 1 and infinity are regular singular points of Legendre's equation. Well, Legendre's equation is the one we've been looking at several times. Depending on how one looks at it. These are the Legendre polynomials, and let me go back to the previous. Well, no, maybe I better stay here. And so the differential equation in self-adjoint form looks like this. And so what we see then is that if we divide through by everything so that we express y double, use this formula to express the second derivative. In other words, here, let me actually show this on this screen. In other words, this equation is minus 1 minus x squared p prime n prime is equal to n n plus 1 Pn. And so what you've got here is minus 1 minus x squared P double prime n. And then when the derivative goes inside there, we have then plus 2x Pn prime equals n plus 1 Pn. I hope I have not made a mistake there. And so now if we divide through by minus 1 minus x squared, we get P double prime n is equal to minus 2x over 1 minus x squared Pn prime. Oh, actually, we've got two minus signs, so that's a plus. And then we get minus n plus 1 Pn over 1 minus x squared. So it looks like that. And that then should be what we have on the right-hand side here. Oh, except that I'm using L instead of N. So to fix that with this Jiffy writer here, I'll make this an L. Oh God, what was that? That was N. That was N. Oh, damn it, I'm going back to L. So this is going to be L plus 1 over that. And so what we do is we say, well, it obviously diverges at x equal to, plus or minus 1. And so we multiply by x minus 1, and we take the limit as x goes to 1. And we're going to write this as, once again, I've got to change here to L. And so if we, unfortunately, I've used P and two different things. In any event, when you multiply by x minus 1, there's perfectly, you just get 1 here, and you get 1 there when you multiply x plus 1 and go to x minus 1. And the same thing with Q, you go to 1. And so what is Q in this case? Q is L plus 1 over 1 minus x squared. And what you do is you multiply that by the thing that makes it finite. And so then as you go to 1 or minus 1, one of those factors, in other words, you take the limit of Q times x minus 1 squared, and that is then x minus 1 L plus 1 over 1 minus x 1 plus x. It looks like that, and so this then is L plus 1 x minus 1 over 1 plus x, and so this goes to 0 as x goes to 1. And so that's where we get 0. And if you do the minus 1, you also get 0. To do the point at infinity, what you do is you set z equal to 1 over x, and then you compute these structures here where, once again, P is, let me just change colors here. P is essentially this. And so what you do then is you set z equal to 1 minus 1, and you take the limit z going to 0 of 2z minus, and now this thing at x equal to 1 over z. So this is minus 2 over z divided by 1 minus 1 over z squared. And so that's this structure here. Oh, and then you divide by z squared. So I'm dividing by z squared. And now this dividing by z squared cancels that 1 over z squared term. And so we get 2 over z minus 2 over z times z squared minus 1, which I guess is this. And we're taking z going to 0, and so the z squared is negligible, and so this actually is 0. So that's this result. And then you take the q, and the q thing, when you divide by z to the 4th, first of all, what is q? Q is effectively 1 over 1 minus x squared. So that's 1 over 1 minus 1 over z squared. And you then divide by z to the 4th. And that's this here. And I kept the yellow plus 1. And when you multiply everything out, you get this structure here. And so you see, as z goes to 0, it diverges. So the point of infinity is singular, even though the p part doesn't make it singular, it's the q part. And on the other hand, if you take the limit not with z to the 4th, but only with z squared, then you get something that's finite. And so the point at infinity is a regular singular point. The next thing is to derive the Rodriguez, not the Rodriguez, the, who was it? For the Frobenius recursion relation. And what you do is you basically, let's see, maybe I should go back to Frobenius here. Oh my goodness, you guys couldn't see that. Well, this is, let's get this damn thing out of the way. So this is, well, it's essentially what was on the other screen, so I guess it wasn't so bad. Maybe I can take this off because I'm not really using it. So then what you have is if you, here, let's see, I should go to I think I'm going to have to show you the screen yet again. So if you go to the Frobenius's solutions, so let me bring it back actually. So what you do is you first write, you multiply by x squared, and you have this structure here. And the reason you do that is that, in other words, you start with this differential equation, and then you set P is x big P, and Q is x squared big Q. And so this equation becomes this. And the reason for doing that is that here you have two derivatives, so they're going to pull down the powers of 2 powers of x, and you replace them this way. Here you pull down 1 power of x and you replace it. So if you set y equal x to the r, the sum of the an's x to the n, then y prime is r plus n an x to the r plus n minus 1. And the second derivative will differentiate this, and what you get is r plus n minus 1 an x to the r plus n minus 2. Now, when you put them back into the differential equation, and remember to multiply the double prime by x squared and the prime by p of xx, what you get then is this structure here. So now, apparently, now if p and q were just numbers, we could get an immediate recursion relation from this. But instead, let's review what happens to find the indicial equation. And the indicial equation is that you set n equal to 0, and you require that this coefficient vanish for n equals 0. Well, that's the equation r times r minus 1, n times p of 0 plus q of 0 equals 0. And that then is a quadratic equation. You get 2 roots. And then to get the recursion relation from this, you have to set p equal to a power series, q equal to a power series in general. And now to go further with that, what you do is you have then this equation here. Whoops, you can't see that. This equation is then just reproduced here. Let me just show you it. Okay, so this equation is here, and that's equal to 0. And now what you do is you put in the sum, you express p as a sum and q as a sum. And when you do that, now let me get this out of the way in case I write something on the iPad. So now what you have is that this is equal to that. And now you want to require that every coefficient, the coefficient of every power of x vanishes. And so what you've got to do then is figure out what, you have to massage the equation so that the, everything is multiplied by the same power of x, and then you take that factor and set it equal to 0. And so what do you do here? Well, what you do then is you set n plus j equal to k, or j equal to k plus k minus n. That means that n can not go any higher than k, and you then find this as the condition, and then you just divide through by the coefficient. You divide through and you see that you get this expression. Now, this is kind of complicated to see. You have to think about it a lot. So let's look at a much simpler case, namely the case where you have just 1 as the initial, as the r equal to 1, and you have, instead of a rather complicated equation here, we just have example 7. It was 739, yes, 739, and so that's actually Legendre's equation. And so once again, you have Legendre's equation here, and substituting r equal to 1, we get this expression here. And now you see what you want is you want to say you need to shift the index n in the first term so that everything is x to the n plus 1. And when you do that, what you do is you let n be n plus 2. And so that gives you n plus 2, n plus 3, a sub n plus 2 for this term. And then you've got the minus x squared there, and that gives you this term. In other words, after you've before you let n go to n plus 2, you've got, let's see, what do you have here? You have one you have an n minus 1, and then you have an x squared. And so gathering all those together, what you've got is an a sub n there and an a sub n plus 2 there. And you can then write that in this form, and then you get this as a recursion relation. So the trick here is you, in this sum, you set n equal to n plus 2, and at least in this part of it, the 1 term. For the x squared term, you've got to actually go the opposite way, because you've got x to the n plus 1, and so you have to let n equal to n minus 1. And then for all these terms, you let, actually, no, when you multiply through by x squared, you get x to the n plus 1. So everybody else is n plus 1. And so you get minus this coefficient, minus 2 times this plus lambda. So that's how that works. This is what you have. And rewriting it, I don't know why I rewrote it. Yeah, it's a little puzzling why I rewrote that. In any event, you then divide through by the coefficient of an plus 2, and you get that as the recursion relation. So then the next problem is, again, Legendre's equation. You want to show that the solutions r equals 0 and r equals 1 are the same. Well, the recursion relation for r equals 1 is actually this. And that means, and so then remember, this series is going to diverge, or in the best case, it converges, but it converges to a function that is not square integrable. And so you require that it terminate, and the way it terminates, if r equals 1, so you go back to this recursion relation. Let's see, which recursion relation? I guess, this is the recursion. Yeah, this is the r equals 1 recursion relation. You demand that it terminate. Well, that means that you want to have lambda equal to j plus 1 times j plus 2 for some j. And so then, so this is the recursion relation. But now if we replace j by j minus 1, we find that the j equals 1, this is the j equals 1 recursion relation. We find the coefficient aj plus 1 is given by, well, let me write it down. And let me switch to a different color here, because this green is kind of anemic. And so here you would have aj plus 1 is equal to j plus 1 minus lambda over j plus 2 j plus 1 j minus 1. And this then is the same as the r equals 0 recursion relation for the coefficient aj plus 2. In other words, then aj plus 2 is, well, it's this one here. And so then it turns out that x aj plus 1, x to the j plus 1 is the same as aj plus 2, x to the j plus 2. Now, the next one is the hydrogen atom problem, and I gave this as a homework problem. So I'm not going to go through it in detail, but I'll just sort of set it up for you. The hydrogen atom potential, of course, is this. and we can write that as q squared over r, where q squared is e squared over 4 pi epsilon 0. So then the Schrodinger equation for the energy is this. And so then what you do is you look at this at big R and at small r. And at big R, what happens at big R? Well, r squared is important. On the other hand, these terms are not important. This term is not important because it's 1 over r. And this term isn't important either. So what you have that's important is that r double prime is equal to just E times this R term. And there's a hidden R squared here. There's an R squared here and an R squared there. And so your equation is R double prime is a constant times R, a negative constant times R. And so R has to be given by this structure. On the other hand, at tiny r, then the term that's most important is this term. And so then the derivative term is LL plus 1R, in other words, this term. And the reason why the 1 over R term doesn't contribute is it's multiplied by R squared. So all of this vanishes for small r. And so you just have the LL plus 1 term. And that tells you that at small r, the wave function, the radial wave function goes as r to the L. And that's a generic thing in quantum mechanics, and it has all kinds of meaning. And in fact, in the earliest nuclear physics experiments, what they saw was that they would scatter protons off nuclei, and they'd find always an S wave. And here they set the experiment up so they were not looking at the electromagnetic interaction, but just the strong interaction, which I get. And of course, the strong interaction is the main thing. The cross-section is much bigger than the electromagnetic one. And so they saw that protons scattering off nuclei, most of the protons would, if you were in the center of mass, the protons, or the rest frame of the nucleus, the protons would come out in just an S wave, same in all directions. And that told them that L was 0. But if L is 0, then that means that the important part of the physics is very, very short distances, so that one gets to an R to the L behavior. And what they realized then was that the strong interactions were very short range because because you just had an S wave. All right, so I'm going to skip the rest of this derivation here and go through this problem. So we imagine that the matrix formed from the boundary conditions, this is the L-jth derivative of the y-kth solution evaluated at xj. We imagine this matrix is non-singular, that is to say it has a non-zero determinant. So then we have these n boundary conditions, and what we're doing here is this repeated index j means that we're summing over j. So we have this no, we're not summing over j. It's that y is equal to c1y1 plus and so forth, cn, yn. And so this is the bj equals that. And so this, if y is this is of the form, you see, in other words, this green equation, what the pointer's pointing at is Bj is equal to Bj is the boundary, it's C1, and well, actually, then it's a sum CK, big Y to the KJ. And so then you multiply by the inverse of Y, and you get that, so this matrix wise, this is equal to CY, and so B times Y inverse is equal to C. And so that's the solution. C is equal to B times Y inverse. This is now showing that the issue is showing the real and imaginary parts of, if the real and imaginary parts of psi and chi satisfy boundary conditions that at A and B that make the boundary term, which is this term here, vanish, then the complex analog also vanishes, which is the complex Wronskian there. And so what you do is you just write the complex Wronskian out, and you get psi is U1 plus I U2, psi star is V1 minus I V2, and the prime means you differentiate both of them. And then you have minus psi prime, so that's U1 prime plus I U2 prime. And then chi star is V1 minus I V2. And all that at B and A. And now if you multiply these together and just write them as real, something real times something minus something imaginary, another imaginary term, then a real term, what you see is that this vanishes if all of the Wronski, if all of the boundary conditions are zero, then the complex one vanishes. But you need this one to vanish, that one to vanish, that one to vanish, that one to vanish. Here, the issue, let me just move this. I'm trying to get everything on the screen. So here, suppose that the real and imaginary parts of psi and chi satisfy the boundary conditions that make, again, the Wronskian vanish. And if the differential operator L is real and self-adjoint, then this equation V VLU implies that one, which is, well, it's the complex version of that. So what we do is we say chi L psi, that's chi star L psi integrated over X. Chi star is V1 minus I V2. Psi is U1 plus I U2, and you have an L here. So then you just, this is the marvelous thing about L being a linear operator. And so you can just separate this out as LU1, LU2, LU1, LU2. But this is self-adjoint, so V1 and this, you got the right boundary conditions, so you can rewrite this as LV1U1, LV2U1, LV1U2, and LV2U2, and then combining them, you see that this is LV altogether star times U1 plus IU2, which is psi, and so this is L chi psi. So this makes the complex operator L self-adjoint. Or it is self-adjoint by assumption, and it's real. I forgot to say that it's real. That's why we didn't need to worry about starring L. But what that means then is that you have chi L psi, that's equal to L chi psi. And this is used very often in quantum mechanics. What you'd have in Dirac notation is something like, chi, some Hermitian operator, like maybe H on psi. Well, this would be E psi chi psi, but you could also write it as H chi psi. And H on chi is E, and E psi, so this would be E chi, chi psi. And so this relation implies that E psi is equal to E chi, unless chi psi vanishes. So the eigenvalues are the same if the inner products don't vanish, or equivalently, well, that's the other side of the thing that one normally proves, which is that the eigenvalues are different if the eigenvalues are different when the eigen states are orthogonal. Here we've got the opposite popping out, that the eigen values are the same. Oh, the eigenvalues are the same because these things are not orthogonal. So it's the same result. It's just one has to get one's knots straight. So we want to show here that if D is the set of all twice differentiable functions that satisfy Dirichlet's boundary condition, that P is continuous and positive, then the adjoint set D star, which is the set of all twice differentiable functions V that make the boundary term vanish for all functions U and D, is D itself. Well, this is what you're given then is, what you do then is you suppose that V is a function that's twice differentiable and that it satisfies the boundary condition. Let's say the Wronskian vanishes in this way for all U. And so what we need to show is that V satisfies the boundary conditions. Well, this thing here is P at B UB V prime B minus VB U prime B is equal to PA UA V prime A VA U prime A. On the other hand, the U vanishes at A and B, and so what we have is that this term vanishes and that term vanishes. So what we're left with is PB VB U prime B equals PA VA U prime A, and the minus signs cancel, and we've got that this must hold even for functions U1 and D, for which the U1 prime of A vanishes and U1 prime at B does not vanish. And then that implies that VB is zero, since P has to be positive. And this must also hold for function U2, for which U2 prime A is not zero, and U2 prime B is zero. And then that implies that VA is zero, since P is positive. Well, this is sort of a long-winded thing. So let's switch and go back to Bessel's equation. Bessel's equation looks like that. Let me copy that down because that's going to disappear. So Bessel's equation is LU is minus XU prime prime. I don't have these things memorized. N squared over XU is equal to lambda XU. So this is Bessel's equation in self-adjoint form. So we want to use the boundary conditions U of 0 is 0 for n positive, and U of 1 is always 0 to show the eigenvalues are all positive. So what we do is we multiply by U of x and integrate. And so we multiply by this equation by u, we get this equals that. And we integrate by parts, we get this boundary condition. The boundary conditions vanish because banish at zero because these are finite, and u of one vanishes, so the other one vanishes. And so we've got that we can toss this away, and we've got that lambda is this over that. And that's a structure that's intrinsically positive. I think we could have gone to this directly just from the previous analysis in the book, which said that the eigenvalues are all ratios of the energy term divided by the normalization term. Well, the normalization term is always positive, and the energy term in most cases is also positive. So this is x goes from 0 to 1, u prime squared then is positive, n squared is positive, x is positive, u squared is positive. This is obviously positive. Let's see, we're actually out of time. Let me just go through this one quickly. These change of variables can sometimes be confusing, so we're going to let u of x equal to jn of kx, and we're going to write that as jn of rho, and we're going to start with Bessel's equation and show that it becomes a different Bessel's equation with rho. So we start out with Bessel's equation, but we're writing u as jn of kx rather than jn of x. And so we have this expression here. So, and then we divide by k to make everything look the same. And then here we can multiply by k, divide by k, so we get kx's everywhere. Over here, we've divided by the whole thing by k, so we have a kx there, and then a k squared goes down to a kx. So now you see if you replace kx by rho, you get exactly Bessel's equation. All right, I think that's enough. Nobody said anything, so I might as well just put the stop recording and make this public. So let me see where is the control thing. All right, so I'm going to